Ladies and gentlemen, welcome to e-learning for gravitation PC3110. Today we are here to discuss what happens in the case of satellite motion when the small body becomes similar in mass to the big body. We have to go all the way back to look at Newton's second law, which tells us that F is equal to ma. In the case of gravitation, you can see that it becomes Fg is equal to mac. When we substitute on the right hand side, we should consider that the question is asking for the period, and so we should use Fg is equal to mr omega squared. Looking at the left hand side, we can substitute for gravity and it becomes gmm over r squared, and we know that that cancels into gm over r squared equals r omega squared. Normally at this point you will collate all the r's together, but you have to be aware that these do not have to be the same distance. It's just that up till now it has been. So what we're going to do is that we're going to take these two and we're going to insert subscripts to indicate the two different forces we're interested in. Let's take a look at the system, a binary star system. The two bodies are of equal mass. For now, let us accept that the center of the orbit is the center of the circle. The gravitation force will not be behaving the same way as the centripetal acceleration. The centripetal acceleration only cares about the distance to the center of the orbit, which we'll label as RC. Gravity, on the other hand, is only interested in the center-to-center distance between the bodies, which is RG. Now that we understand what these distances are, let's take a look at the equation again. We cannot simplify the equation any further. We have to put this in, we have to use these equations and substitute in the values that we have. Okay, what we have is Rg, which is the center-to-center distance between the bodies, and Rc, which is distance from body to the center of the orbit. So that looks reasonably clear, except this is what you're thinking right now, and this is probably how you look. It's okay, there is no need to panic. What's the center of orbit of a system? If you let something orbit freely, what happens is that it orbits its collective center of mass, which you have already learned in the topic called momentum. In this particular case, take it from me that it is at the center of the circle, okay, and as a result, that's comparatively easy. Okay, you can do the calculation in your own time. What if the system is not symmetrical? For example, one body is 3 times the size of the other. Can you still calculate the center of the system? Well, of course you can. I mean, otherwise you wouldn't be able to get very far. Can we do it simply without having to go through the full complication that we did for momentum? Again, the answer is yes. But we're not going to use what we did before. We are going to use the circular motion information. Using Newton's third law, we know that the magnitudes of the forces are the same, that F1 is equal to F2. Because you're only dealing with magnitude, we're not going to bother with plus minus signs. We also know that each body orbits the center of gravity and their periods are identical. Based on that, we can substitute on left and right using the mr omega formulation of Newton's second law, giving us mr omega is equal to mr omega. If you're sitting there with your eyes closed, you won't be able to hear the difference, but we are using uppercase to indicate the big mass and lowercase to indicate the small mass. Since the omegas are the same, they will cancel, and we get Mr. is equal to Mr. Which is rather helpful. And what we're going to do now is we are going to identify, again, big R is the distance from the big mass to the center of the orbit, and small r is the distance from the small mass to the center of the orbit. If you add big R and small r together, you'll get Rg, which is the center-to-center distance. It's the same for both. We rearrange and we get the ratio of masses is the inverse of the ratio of the distances. Does this look right? Well, let's consider the binary star case. Since these two are the same, these two would be the same, and the center of mass is in the center. If you consider a seesaw case, okay, from all the way back in semester 1 or maybe back in primary school, you will find that this looks exactly the same, and we can carry on. Now, let's consider the case where one body is much larger than the other. Like, for example, a satellite around the Earth. In such a case, you can see that the ratio of the satellite's mass to Earth's mass is 0. And therefore, the ratio of the Earth's distance to the center of gravity to the satellite's distance to the center of gravity is also 0. What does that mean? It means that the center of gravity is the center of the larger mass. In such a case, therefore, Rg will be equal to Rc. We can then collate them all together into this form, and that gives us R cubed is proportional to t squared, which is what you people have learned as Kepler's third law. We started with this scenario. We then gave you a situation where we were no longer able to keep these together. From there, and using basic principles, we discovered certain principles, certain rules that we could use to apply, and we applied that back to the original case. We ended up with what we started with, which is what you would expect. You have now seen a bit more about gravitation than you would have before, and you've seen a bit more than what your compatriots outside of NUS High will have learned. Please take this knowledge away with you because you will find it useful again. Okay, please take this, go off and do the discussion questions and the assignment questions given to you, and prepare yourselves for the common test. Thank you.